Friends, let us continue our discussion on complex reactions, and to recap, we saw in the last class various examples where reactions do not occur as simply one step process, but typically complex reactions involve large number of reactants, large number of products, large number of reactions which connect reactant to products. In the process, there are lot of intermediates in the reactions that appear, and we are now concerned about how do we determine the kinetics of such processes. So, that is our ultimate objective, that how do we determine the rate at which reactants are going to product or rate at which products are being formed when we have such large systems to deal with. What we are started with is construct very simple complex reactions, such as we considered last time parallel reactions, series reactions and so on, and we were looking at parallel reactions and what happens when you have more than one reaction. You usually have conversion is not a sufficient criteria for design of reactors, because let us go back to our example and let us say that we have this desired reaction A1 going to A2, which is accompanied by an undesired reaction A1 going to A3, then conversion of A1 alone is not sufficient for design of reactor, because it does not tell us anything about how much of that A1 is going to actually A2, because that is what we want as a product. So, we have to define what we term as selectivity, and in the last class we defined two different kinds of selectivities. One, instantaneous selectivity small s2, which is a ratio of rate of the desired reaction to the total rate of consumption of A1, that is both in desired as well as undesired reaction. So, R1 by R1 plus R2. We also defined overall selectivity. For example, if you have a plug flow reactor, then overall selectivity is the exit molar flow rate of the desired product to exit molar flow rate of the total products that are coming in. Let us now see how these two quantities are related to each other and how the design of reactor now gets influenced by ideas such as selectivity. So, let us work this same problem, but now let us say that we have a plug flow reactor. We have a plug flow reactor in which these two reactions A1 going to A2 at a rate R1 and A1 going to A3 at a rate R2 are taking place, and our first reaction and the product is a desired product A2, but there is unfortunately an undesired product also coming into the picture. So, we make another assumption that volumetric flow rate is constant. So, the selectivity capital S2, which is defined in terms of molar flow rates, will also now can be defined in terms of concentrations. Because it is a volumetric flow rate, we have assumed constant for sake of this illustration. Now, we also have stoichiometry, and we know that for every mole of A1 that is consumed, A2 is formed, same is the case with A3. So, the concentration of species 2 and 3 put together must be same as that of A1 that has got consumed. So, if C10 is the concentration here at the inlet and C1 is the concentration in the exit, then C10 minus C1 must be C2 plus C3. Once again we have made a small assumption that there is no A2 and A3 at the inlet of the reactor or at the entry point. That is a reasonable assumption, because normally you would not want to feed the reactor with the product itself, because where do we get that product? Okay. So, this is our overall selectivity, and now let us try to see how this selectivity, overall selectivity, is related to the point selectivity. Okay. So, our point selectivity as we defined earlier was R1 by R1 plus R2, which if we use our mass balance equations, for example, U dC1 dz as the consumption of species 1. So, that is minus R1 minus R2, and U dC2 dz is R1. Our normal plug flow reactor mass balances. This point selectivity, which is R1 by R1 plus R2, is nothing but dC2 by dC1 minus. So, that is our point selectivity, okay, which is S2. So, now I can write dC2 by dC1, which is S2 minus C1 dC2 by dC1 is S2, and then I can therefore write C2 as integral C10 to C1 S2 dC1, and therefore write, let me therefore write C2 by C10 minus C1 is 1 over C10 minus C1 integral S2 dC1 C10 to C1. See, this is nothing but my overall selectivity. So, my overall selectivity is related to my instantaneous selectivity small s2. This is what happens in a plug flow reactor. Okay. What happens in a CSTR? You can once again write the mass balances for species C1 and C2 and rearrange the equations, and we will get C2 by C10 minus C1 as R1 by R1 plus R2 or nothing but S2. Okay. We will get equal to S2. So, we have this equation for plug flow reactor, we have this equation for CSTR, and question naturally we would like to now ask is which of these two reactors give you better selectivity. To answer that question, we need what are these R1s and R2s. So, let us say my R1 is K1 C1 raised to Q1 power law kinetics with order Q1, and for second reaction it is K2 C1 raised to Q2 again and power law kinetics. So, with these two rate equations, I can now write selectivity, point selectivity S2, which is R1 by R1 plus R2. So, if I do little bit of manipulation, I will get this value as 1 by 1 plus K2 by K1 C1 raised to Q2 minus Q1. So, this is my point selectivity. I know it changes as concentration C1 changes, and these are the two design equations which tell me what is the selectivity in a plug flow reactor and what is the selectivity in a CSTR. So, now let us look at how this system behaves for different scenarios. So, we have this once again same reiterating the same idea that for CSTR this is my selectivity, for plug flow reactor this is my selectivity, and we just now wrote that selectivity S2 is 1 over 1 plus K2 by K1 C1 raised to Q2 minus Q1. If R1 and R2 are expressed as power law kinetics having orders Q1 and Q2. So, now how selectivity changes as the concentration of C1 is changed will depend upon these values of Q2 and Q1. So, let us look at that behavior once again in the same plot of C1 0 minus C1 against selectivity. Let me write the design equation once again. For plug flow reactor and S2 equal to small s2 or is equal to R1 by R1 plus R2 for CSTR. Okay. And my selectivity is 1 by 1 plus K2 by K1 C1 raised to Q2 minus Q1. So, let us examine what happens to our selectivity as function of concentration of C1, but instead of looking at C1 we are going to look at C1 0 minus C1. The simplest case is Q2 and Q1 are same, that means the orders with respect to A1 going to A2 and A1 going to A3, these are the orders Q1 and Q2. If both are equal, then selectivity is independent of concentration, and that is represented by this violet color line when Q2 and Q1 are same. Let us consider a case where Q2 is greater than Q1. Okay. That means, the second reaction order is higher than the first reaction order. If that is the case, then Q2 minus Q1 is positive. So, as C1 increases, the selectivity should decrease, and C1 increase in our case is in this direction, because this is C1 0 minus C1. So, C1 increases in this direction. So, as C1 increases, we get increase in the we get rather decrease in the selectivity if Q2 minus Q1 is positive. This is the case shown with this green line when Q2 minus Q1 is positive. The third thing now you can expect is if Q2 minus Q1 is negative, we should get a behavior which is shown by this blue line over here, So, now we have various behaviors of selectivity as a function of C1 0 minus C1. Now, let us look at what happens to a plug flow reactor. For a plug flow reactor, again the design equations are independent of the kinetics. They are the characteristic of the flow conditions and what kind of reactor we have. So, for plug flow reactor, by now you would have guessed is nothing but the area under the curve over C1 0 minus C1. So, let us say if our Q2 and Q1 are same, S2 is independent of selectivity, then the area under the curve or area of the rectangle. Why are we interested in area of the rectangle? This CSTR line is nothing but the area of the rectangle, and PFR is nothing but represented by the selectivity is represented by area under the curve. So, let us say for this particular concentration C1, whatever that value is, the selectivity for plug flow reactor is given by this shaded curve, which is for the case of Q2 minus Q1 greater than 0, which is our green line and plug flow reactor as the area under the curve. But what happens if it is actually not selectivity, because we have to not divide it by 1 over C1 minus C10 minus C1. So, if you do that, but the area gives you the representative value. Now, what happens for a CSTR? This is nothing but this particular value, which is actually the area under this curve, under this rectangle, divided by C10 minus C1. And you can clearly see here that if Q2 is greater than Q1, then what happens? Selectivity in a CSTR is higher than the selectivity in a plug flow reactor, which means that as far as the selectivity is concerned, CSTR is better than plug flow reactor. But what about conversion? So, just let us put some numbers. So, suppose Q1 is 1, Q2 is 2, we know that for power law kinetics with positive values of Q1 and Q2, conversion is always highest in plug flow reactor. We discussed that few sessions back. That is because the concentration suddenly decreases in CSTR, whereas the decrease is gradual in plug flow reactor. So, conversions are better in plug flow reactor compared to CSTR. But what happens when it comes to selectivity? The selectivity in a plug flow reactor is now worse than the CSTR, or CSTR is better than that in the plug flow reactor. Or what it implies is that for conversions PFRs may be desirable, but that does not guarantee high selectivity. For achieving high selectivity, CSTR is better than plug flow reactor. And why is this happening? We go back to this particular kinetics. See, the rate of first reaction is K1 C1, let us say Q1 is 1, and second reaction is K1 C1 square. See, we are looking for making more of A2. So, what happens in a CSTR? CSTR concentration is low compared to that in a plug flow reactor. Lower concentration, because it is squared in the second reaction, reduces the rate more or that as compared to when the order is 1. That means, comparing between high concentration and low concentration, the concentration has more effect on reducing the second reaction than the first reaction. Why? Because in the second reaction concentration is squared. So, square is always the contribution of a square is always higher than contribution of a linear term. So, that applies to reduction also. So, reduction is higher in rate is higher for the undesired reaction and whenever there is a reduction, higher reduction in undesired reaction rate, that means that is desirable. So, CSTR has lower rates of second reaction compared to their counterparts in a plug flow reactor, and as a result the selectivity in a CSTR is better than that in the plug flow reactor. Now, we can argue in a similar manner what must be happening for Q2 minus Q1 negative. Once again, so for the same concentration, area under the curve now for a plug flow reactor is higher than the area of the rectangle somewhere over here, area of this rectangle which is for CSTR. That means, for this particular case CSTR selectivity is lower compared to plug flow selectivity. That means, both from the point of view of conversion and selectivity, plug flow reactor is better than stirred tank reactor for this particular case, when Q2 minus Q1 is a negative quantity. So, for example, a situation where Q1 is 2, Q2 is 1, and you can now argue it along the same lines as we saw for this particular example, because one is square, other is linear term. So, which one will give you higher rate of favorable reaction. So, this particular example tells us that how reactor design criteria change when you have complex reactions. Remember, we considered a very simple prototype of a complex reaction. We did not have more than 3 species, only 2 reactions, but with that alone it is sufficient to illustrate that things are not straightforward anymore. There has to be a compromise between conversion and selectivity when it comes to such reactor behaviors. Let us continue our discussion with such simple prototypes, but this time let us take example of a series reaction. So, we have 2 reactions, A1 going to A2 and A2 going to A3, both proceeding at rates R1 and R2. This should read as R2, rates R1 and R2. R1 is K1 C1, R2 is K2 C2, and we would, let us, for sake of argument for this discussion, let us say that we are conducting this reaction in a batch reactor. If we are conducting this reaction in a batch reactor, then we can write the mass balance equations for the batch reactor, which we had seen earlier, again assuming constant density as minus R1 or minus K1 C1, dC to dt as K1 C1 minus K2 C2 and dC3 dt as K2 C2. So, these are our mass balance equations for our batch reactor. Now, let us see how does this reaction progresses in a batch reactor. So, to do that, we are going to say that we started this reaction with some quantity of A1 to begin with. So, what we are seeing here in this particular plot is time axis on the x and y axis represents concentration of 3 different species. Red or orange is A1, green is A2 and violet color is A3. So, we started this reaction with some quantity of A1 and nothing of A2 and A3. To monitor the progress of this reaction, we measure its concentrations, and what you see pictorially in this particular graph is the simulation of these equations for value of ratio of K2 by K1. Now, it turns out that if you make these equations dimensionless, then time can be represented as K1 t. So, this is actually not real time, but some K1 into t. So, if you make these equations dimensionless, a ratio appears in the mass balance equations of K2 and K1, and we call that ratio as alpha, and this example or this particular graph is for value of alpha equal to 0.1. We will do it for different values of alpha little later on, but at this point let us look at what happens when we have value of alpha equal to 0.1. So, what we are seeing here is A1 is going to A2. So, A1 is continuously decreasing as time increases. So, we have continuous decrease in A1. Okay. So, this is my A1. What happens to A2? A1 goes to A2. So, initially A2 builds up, but A2 is also going to A3 for this series reaction. So, after some time the rate of generation of A2 falls short of rate of consumption of A2, and therefore, there is a net consumption and A2 starts going down. So, this is what happens with A2. What happens with A3? You can expect as soon as A1 is formed, A2 is formed, A2 is going to A3. So, there is a gradual build up of A3 as the reaction proceeds. So, this is my A3, and that behavior explains how these reactions proceed in the Now, let us bring in a more realistic situation where we say that A1 going to A2 going to A3 is my reaction, but my main product or desired product is A2, and A2 going to A3 is an undesired reaction. I do not want it, but it is inevitable that it happens in the reactor. So, now what we will do is the same representation of concentration versus time. We will now try to see what happens to A2, built up of A2 as A1 is getting converted, or in other words, we will now see the same behavior, but instead of time, this time on x axis we have conversion of A1. And on y axis we have yield of A2. So, we are looking at yield of A2 versus conversion of A1. How do we define yield? Suppose we are doing a batch reaction, this is nothing but C2 by C10, and how we define conversion? We had done this earlier. We have defined conversion as C10 minus C1 divided by C10. So, we are looking at these two behavior, and what do we see here? As conversion is increasing, the yield is also increasing. So, that means as more and more of A1 is getting converted, we are getting more and more of A2, but this increase is halted at certain value of conversion, let us say this particular value, where it reaches the peak, and any conversion of A1 beyond this value, the yield of A2 actually decreases. A2 actually decreases from here to here. So, it is increasing from here, from 0 conversion to this particular value, let us say some value of conversion x star, and beyond that value it is decreasing. Why is that happening? If you recall the behavior of this system from the previous plot, A1 is getting continuously converted to A2. So, the conversion of A1 is continuously increasing. But what is happening as a result of more and more A2 accumulating in the system is that more and more A2 is now going to A3. A2 is going to A3. So, beyond this critical point, instead of A2 accumulating in the system, it actually is now consumed, and we are seeing formation of more and more of A3. So, if this is kind of system that we have with us, then it does not make any sense to go to design reactors for more than critical conversions such as this X star. Let me relate this to what we saw by way of example few slides back, that is, earlier we considered this example of hydrogenation of oil, and we saw this behavior, what happens by way of conversion versus yield. This particular behavior is very similar to what we just now saw when we considered the reaction, a simple kind of reaction such as A1 going to A2 going to A3. That means that hydrogenation of unsaturated oils must have somewhere in the reaction scheme reactions of the type A1 going to A2 going to A3. So, which results into this kind of conversion. So, two lessons we learnt when it comes to complex reactions. Lesson number 1, that when we have complex reactions, conversion is not the only criteria for design. We have to worry about yields, selectivities and so on. And when it comes to designing for selectivity, it is not necessary that a plug flow reactor will always be better than a stirred tank reactor, or in other words, the choice of reactor for maximizing selectivity is not necessarily same as choice of reactor for maximizing the conversion. So, there is a balance that need to be then sought. What do we prefer more, the selectivity or conversion? And if you recall my first session, we are more and more concerned about not making undesirable product. So, it means that we are more and more worried about selectively making the product or enhancing the selectivity rather than the conversion. The second lesson that we learned from this particular example is that maximizing conversion is not always the criteria, because maximum conversion often gives lower yields compared to restricted conversion over here. Let us consider this same example of A1 going to A2 going to A3 and illustrates another concept which is often used when we try to analyze complex reactions, and this is the concept of rate determining step. What is this concept? This concept is very simple. We use this all the time in our we see this or we experience this. You imagine a relay team. we are participating in 4x100 Olympic team, Olympic event, let us say, or let us say Commonwealth event, which is going to be shortly held in India. Now, we know that a performance of the relay team is determined by the weakest runner in this team. It is not determined by the fastest runner. The fastest runner may try to improve his or her performance by running even faster, but that is not going to improve the team performance. What is going to improve the team performance is if the slowest of the runners or of the teammates improves his or her performance, and that will improve the performance of the team. We know this. In fact, we should know this more so if you drive in India. You are often seen people driving very fast whenever they see an empty road, but they do not realize that driving faster on an empty road is not going to improve your time to go from point A to point B, because the bottleneck is somewhere else, the traffic jam is somewhere else. So, you will end up taking the same amount of time even if you try to go very fast on an empty road. The point I am trying to make is that it is the slowest step which always determines the performance of any process when there are more than one process, when there is more than one runner, when there are more than one road we have to travel, the empty road does not determine the travelling time. Let us go back to our reaction kinetics and see how this applies to our reaction kinetics, and we will see this with an example. So, let us go back to this A1 going to A2, A2 going to A3. We are looking at the batch reactor and same dimensionless time, dimensionless time K1T and concentrations of A1, A2 and A3, but this time I am going to look at this system in a slightly different way. I am going to look at this system saying that A1 is my main reactant and A3 is my main product that I am interested in, and A2 is in some intermediate which is appearing in this reaction scheme. Recall, we said that complex reactions start from reactants, end up in products, but there are a lot of intermediates in between. So, now let us treat A2 as an intermediate, and we are now interested in looking at what is the rate of formation of this product. What is the rate of formation of this product? So, we are looking at dC3 dt. Since it is a batch reactor, that directly tells me the rate of formation of this product. So, let us look at the same results. We saw these results few minutes back. For alpha value, that is the ratio of K2 by K1 to be 0.1, let us look at A1, A2, A3. So, we saw this earlier. So, A1, A2, A3. We see that A1 decreases, A2 first increases and then decreases, and A3 is continuously decreasing. Now, if you look at this figure more closely, and if we look at particularly what is happening after this particular time, some time over here. Okay. Let us not worry about what happens from the start of the reaction up to this time, but for the time for which the product is appearing in the reaction quite significantly. So, we are looking at this part of this particular part of this curve, and what do we see? We see that the rate of appearance of A2, that is this violet line over here, the rate is almost similar to the rate of disappearance of A2 that is this slope is in magnitude same as this slope, only the signs are different, or in other words dc3 dt is almost equal to minus dc2 dt, because A2 is consuming. So, we have to put a minus sign there. Okay. So, this is what happens when alpha is 0.1. Let us now look at what happens when alpha is 5. The same reaction, everything is same in the batch reactor. So, we are now carrying out this reaction when alpha is 5. So, once again as before A1 is decreasing. In fact, it is same as before, because we are looking at dimensionless time K1 into T. A2 is also initially increasing and decreasing, qualitatively same behavior as before. This is my A2. But let us look at what happens to. So, let me go back over here. This is my A1, this red line over here. I have A2, and let me go back and look at what happens to A3. A3 is of course qualitatively same behavior, is increasing. So, whether it is alpha is 0.1 or alpha is 5, that is this ratio of K2 by K1 is 0.1 or 5, qualitatively behavior is same, but quantitatively there is a difference. I think I need not repeat myself, but write this straight away, that in this case we see that dc3 dt is almost same in magnitude as dc1 dt, but with a negative sign. So, this time the rate of formation of C3 is same as the rate of consumption of A1 or C1, okay, when alpha is 5. In my previous example, when alpha was 0.1, dc3 d2 was equal to minus dc2 d2. So, this is for alpha equal to 0.1, and let me write down what happens when alpha is 5. Alpha is 5. Let us examine the value of alpha. What does alpha mean? Alpha is a ratio of second reaction rate to the first reaction rate. So, between these two, alpha is lower in the first case, that is 0.1, that means second reaction is substantially slower compared to the first reaction. And what happened to rate of product formation? The rate of product formation is determined by now the second reaction, because dc3 dt is dc2 dt. That means, rate in this particular case is determined by second reaction. This on the contrary, when alpha is 5, the rate is determined by first reaction. What happens when alpha is 5? Alpha is 5, first reaction is slower than the second reaction. So, in either case, the rate of the reaction is determined by the slower of the two reactions. If first reaction is or rather second reaction is slow, the rate of formation of A3 is determined by the second reaction. If first reaction is slow, when alpha is 5, the rate is determined by the first reaction. Again, the idea that there is a rate determining step which determines the rate of conversion to product or rate of formation of product. This is a very useful concept, and we will be using this concept time and again when we try to analyze complex reactions. That is, when you have large number of reactions, we will make an assumption that one of these reacting step is the slowest of all. That is my rate determining step. In fact, it is also referred to as RDS, rate determining step, RDS. And then we will have to make certain other assumption as far as the other reactions are concerned. So, what we are saying is we have let us say 10, 15 whatever number of reactions, one or it could be more than one, but these one or more than one maybe two steps or reactions are very slow compared to all the other reactions. So, we will therefore then say that the rate of conversion of reactant to product is then determined by the rate of these slow steps, 1 or 2 whatever that may be, and then we will try to determine the kinetics of process by further applying certain other simplifying assumptions to the remaining steps, and this will be our logic that we will follow for determining the kinetics of complex processes. What are those assumptions for remaining fast steps? We will see that in the next session. Thank you.